Uncomputability, quantum control, Diophantine equations, and it sounds pretty cool, so
thank you for the opportunity to present this project. So actually, so there's two funny things I want to say about it, just unrelated to science. First of all, when I was writing the abstract and title, I did this in Microsoft Word, and actually it changed, the first word actually. It's because in my program it says uncountability of quantum control, and it's of course not the same thing as uncomputability. It's related mildly, but it's not the same thing by no means. So it's interesting that actually Microsoft Word does not recognize the word uncomputability. So I guess in the world of Bill Gates, etc., everything can be calculated, which is of course not the case. So this is quite interesting. And of course, thanks Mark for pointing out some other typo. Now, so this work done in collaboration with Alexander Pechin. He's a group leader at Russian Academy of Science in Stockholm Institute. It's kind of like advanced institute for Russian version of Institute for Advanced Studies. All like famous Russian mathematician work there, like Falk, Krylov, Holevo, etc., etc. I mean, there was still work there. So, and also another unrelated to science, related to this talk, but unrelated to the science of this talk story, that I was invited to give a talk in Moscow actually about, Alexander invited me to give a talk about this, and on my way, it was last fall, and so I combined a bunch of trips, visits in Europe, and so I was that was my last kind of trip was supposed to be my last talk, and I was in Poland at the time, and so I met a friend, and we got like pretty intoxicated, and I was not checking news for like for a day, and then I arrived to Moscow, and I'm actually a citizen of Ukraine, so I can travel, like freely travel to Russia with Ukrainian passport, and then I arrived to Moscow, and they don't ask me any questions on the border, not ask me where do I live, so I live in the US, and so I come into my hotel, and I open the news, and I see like Ukraine is like again there's a like active escalation of the war with Ukraine, and I was like, oh my God, what should I do? Should I run or not? So it's good not to check news actually when you travel. Sometimes. But it was a great stay actually. I enjoyed it a lot. Anyway, so let's go to the science finally. So basically, when you talk about computability, the first thing that you will come up is sort of Turing machines. That's the typical theoretical framework. However, there are different ways of talking about computability, and I think two talks ago was mentioned lambda kernel, so that's one of the way of doing it. Good news for us is that any modern computer language is Turing complete. So if you have some piece of computer code, actually, it's a basically theorem. You're writing a theorem also. And now, did you guys know that even LaTeX is a Turing complete language? Because it has you can do lambda calculus in LaTeX. So now, as I said, there are many different ways of doing representing computing, but irrespective of the representation, there are problems that cannot be solved by computers. So computational problems that cannot be solved by computers. And this was, of course, discovered by Turing, and it's called halting problem, an example of such a problem. It's a basically question, it's a decision question whether a given piece of a program will ever stop or not. And so what does unsolvability means here is that uncomputability means that there is no computer program that can take as an argument a specified program that makes the decision. Actually, have a nice proof, Python proof of it. So if you have questions, you can ask. Oh, that's the proof. So now here's some examples. A bunch of Python programs, Python functions. So obviously this is never going to stop, right? This is just infinite loop. This will actually stop after making 10 increments. Likewise, this one is also going to stop. These two are equivalent, right? So what about this one? Can somebody guess whether this is ever going to stop or not? Of course, the only thing you need to know is GDC stands for a greater common divisor.
Some unproven conjecture.
Yeah, it's okay, exactly. It's actually, oops, what did I do?
You're back.
Back, okay, oh.
Yeah.
So this is actually, if we know the answer to the question whether this program holds or not, it's equivalent to solving the Riemann hypothesis. So it's pretty cool, right? That's such a small piece of code. You know, that's the answer to the Riemann hypothesis, if it ever stops or not. Many important problems, not all, but many important problems, mathematical open problems, can be reduced to like a halting problem. This is why it's important. Now, today in my talk, I would like to talk about different way of representing computability, and I think it's much more interesting for physicists with the, you know, maybe not that mathematically savvy physicists like Mark, you know. So it's Diophantine equations. So it turns out that Diophantine equations, you know, we believe that they were invented by this Diophantine of Alexandria. They're really old object. I mean, they're from 3rd century, and it turns out that solving them is equivalent to actually doing programming. So let me just introduce quickly Diophantine equations. So those are polynomial equations with integer coefficients, and we would like to find solution in integers. So the last part is very important. So let's just take an example. So here's the polynomial equation. You see it's a polynomial equation with integer coefficients, and we would like to find solution in integers. So it turns out that this equation has a unique solution. Now, you can take another equation from high school and related to Pythagoras theorem. So for example, this equation is also Diophantine equations, but it has infinitely many solutions. Here's an example. And here's another very famous Diophantine equation that took more than 100 years to solve, right? Or even more than 100 years to solve, that has no solutions. And the key here is that we look for only integer solutions. That's what's important. Because if I were to give you the polynomial equation has always solutions. There's always solution in complex numbers. But integers, that's a different story. Now, because of sort of Diophantine equations appear in math all the time, this dude actually formulated lots of 23 problems, and one of the problems was about these type of equations. David Hilbert asked, using modern language, of course there was no language of algorithms at that time yet. So he says, is it possible to have a computer program that would make a decision whether a given Diophantine equation is solvable or not? So the key here is that Hilbert does not ask a question, can we have a computer program that finds a solution, that prints out a solution to the equation? It just makes a decision whether it has a solution or not. Right? So it's a much more weaker question, weaker statement. So it turns out that this problem is not solved. Basically, there is no computer program that takes as an input the Diophantine equation and makes a decision whether it's solvable or not. And basically, the way how it's done, it turns out that this question is reducible to halting problem. And there's excellent documentary about this stuff. And it's actually you can see it on YouTube for free. It's quite interesting, and actually there's also an amazing book about this story written by Yuri Matisevich. The person actually put the last at the age of 33, he actually solved it. He put the last break in this Hilbert 10th problem. Very, phenomenologically well written book as far as mathematicians are concerned. So let us actually. My personal interest in the subject came from this book. Actually, I read about this Hilbert thing and the Diophantine equations, and then I decided to read. I didn't quite understand everything, so I pick up this book and start reading, and I couldn't stop. And I said, so since I wasted so much time, I should write this in paper, so that you can justify it to myself. So obviously, I was not the first one to recognize the beauty and sort of this Diophantine language in quantum physics. So it's actually let's say that we have a Diophantine equation. These are unknowns, right? Again, it's a polynomial equation with integer coefficients, and we look for x's which are integers. So it turns out that this actually equation can be kind of embedded into if it has n unknowns, to n boson problems, mapping to n boson problems. So let's take a very n non-interacting bosons. And then this equation has a solution if and only if the following Hamiltonian has a zero ground state. Right? It's very easy to see why. Since this is these guys commute, this is just a number operator, right? So you can see this, right? This is a number operator, and so this is a total of n particle, n boson Fock state. So this is actually, this is zero by definition, and this state solves. This state becomes a zero ground state of this Hamiltonian if and only if this combination is actually solves this Diophantine equation, right? So it's a very nice mapping. Is this clear? So it's a pretty nice idea. So it was meant by Kio in quite a long time ago. I have to say that he actually, unfortunately, I think it was quite unfortunate that he tried to use this statement to say that algorithmic computing would be able to solve problems that cannot be solved by classical computers, meaning like that it goes beyond Turing machines. So, since you can start with a kind of simple ground state, right, and algorithmically turn on into something like this, right, something generic, and so this result found a lot of controversy. This interpretational result found a lot of controversy, but I think this mapping, is 100% legit. There is no controversy. Now,
why is the square necessary?
because we do not know d, right? It can be negative or positive, right? So you could take negative. The values could be positive integers or negative integers, right? So I want to make sure that this thing has a ground state, right?
Yeah.
So now, using again, it's sort of in the context of this debate about Turing, whether we can go beyond Turing machines, Turing computability in quantum physics. Smith actually showed that actually turned Kio's argument upside down and say that actually his mapping means that computing the ground state of n interacting bosons is actually not solvable, non-computable. So this is kind of amazing, right? The most fundamental quantity of physics or ground state is basically not computable. So this was published, as you can see, in a not so prestigious journal as Nature. By the way, it's a real Nature. Where actually a group from Munich actually published that the decision problem, whether they have a fermionic Hamiltonian, and whether this fermionic represents a gapless state or gap state, meaning that whether the ground state energy and the first state energy are degenerate, it's also not decided. Whether this is like 100 pages proof or something, whereas this is like a couple of lines using the Kio's argument for bosons. So you see, this is kind of lots of interesting things going on with uncomputability in quantum physics. Now, so here's our modest contribution to this discussion. Actually, we would like to, both me and Alexander actually are coming from the same group at Princeton, which was by Professor Rabbits, where quantum control is sort of the main focus. And so we ask ourselves a question: is quantum control actually a computable problem? And the answer is no. And let me just present one. So what is quantum control? Quantum control is a problem of finding a way of steering dynamics such that at the end of the quantum evolution we get the state with desired properties. Right? So that's, and we want to do it usually in optimal fashion. We want to do it as fast as possible or as energy efficiently as possible. Now, so let us introduce a kind of toy version of quantum control problem, which we shall call digitized quantum control. So first of all, I have to say that quantum control, there are two main versions of quantum control. First one is purely coherent, where we want to find a unitary evolution, synthesize unitary evolution to achieve optimal task. But there is also so-called reservoir computing, where we actually say, okay, it's enough to have some kind of, we allow for some kind of degrees of openness, so we want to synthesize Krauss maps. So therefore, let us say we are given a bunch of Krauss maps, Krauss transformations, phi I, and we are given some quantum state in the initial state rho, naught, and we are given some observable O, Hermitian observable O, and so we would like to find a sequence of P's, P1, P2, etc., P, such that the expectation value of O at the final state is 0. So once again, so we have initial quantum state, and then you discretely apply. This is why it's called digitize. Digitize, transform it like first some Krauss map, then not different Krauss map, etc., etc. You do it capital P times, and then if the expectation value of the final state with respect to observable O is 0, that's what we call. We solved the problem of digitized quantum control because we found a policy, a sequence of integers, such that the final state is 0. Yes, and I have to say that, by the way, that in practice, also this is, so why it's integer once again? So because we have some discrete sequence of these phi i's, and the sequence of application is crucial, right? It's not, the sequence, you cannot permute it in general. The sequence is important, so it doesn't have to be, it's not just 1, 2, 3, it's some permutation of indices, permutation with repetition. And one more thing is that not all sequences could be considered to be allowed due to some engineering reasons. So therefore, in fact, the sequence of integer needs to be from a set of allowed solutions. So was this clear? This kind of basically we will prove that this one is super easy to prove for this problem that this is not solvable. This is not computable. Okay, but you can say, okay, so who cares? I mean, this is some kind of a cook up a problem. Some specific problem which is some expectation value of something to be 0 at the end. But it turns out that actually generic optimal quantum control problem is reducible to a sequence of these problems. So if you prove that that one is, if digitized quantum control is uncomputable, optimal quantum control problem is also computable automatically. There are some interesting. Properties that you can read while I'm checking time. Okay, 16. So for example, it turns out that in general case, it's not enough to have finite degrees of finite number of steps to solve this problem. Actually, it's basically the solution that find this solution to digitized quantum control problem with a finite policy size is actually measure 0 solution. But you can do it always with arbitrary accuracy. So if you say, okay, I don't care about 0, I care about something like absolute close to 0, then there's always a finite solution. Now, so we are going to show. Yes?
Sorry. Do you know that solution scales with epsilon?
No, but pretty bad, right?
Okay.
Probably. But you don't know.
Right.
So yeah, we do not investigate this question. It's just a kind of. I think it's going to be. We actually that proof we invoke Kitayev's theorem about existence of universal gates. So that's basically probably the same scale. It has exactly the same scale.
Okay. That's supposed to be pretty good.
No, but this is cool. This is what I mean, right? I told you the first property is that this problem is equivalent to ordinary quantum control problem, right? So obviously, so it should have the same scale. Like if it's equivalent, it cannot be better, right, or worse. Now, so what? So we are going to show that solving this problem is equivalent to solving some Diophantine equation. And we're going to show that solving any Diophantine equation can be mapped into solving this problem. So in that sense, we establish an equivalence between quantum control and solving Diophantine equations. So the first part is a reduction of this quantum control problem to the Diophantine equation. It's actually done so trivially that I'm embarrassed to present this. Actually, we just need to remember an object which is called Lagrange interpolation polynomials. The only difference is that this is the only difference from Lagrange interpolation polynomial by the fact that the argument is a matrix. And so it's selected in such a way that it accepts an integer argument and returns a Krauss matrix. So then actually this expectation value is being represented this way, and where each of these things is a polynomial degree n. So it's a product of product of length p, basically p products of polynomial degree of n, therefore this is actually Diophantine polynomial. Right? This is itself. Plus, what's cool is that also by an engineering constraint that you say, okay, not every sequence is allowed, but only some sequence is allowed due to some engineering reasons, also introduces a term which is, again, Diophantine equation. So the whole problem is actually Diophantine equation. So therefore, we established that any quantum control problem is equivalent to this Diophantine equation. Now let's do the opposite, and the opposite is a little bit more interesting. The opposite, we sort of invoke Keyes argument. So this is actually how solving any Diophantine equation is equivalent to doing quantum control. So let me just quickly go back to Keyes argument. So you see, his solution required a preparation of a cat state in the Fock space, and it's an occupation number state. So from a practical point of view, from an experimental point of view, this is really bad. This is really bad because usually these axes can be quite large, and to prepare Ryan can testify, I know Mark on the left, right? That preparing quantum state with a large fixed value of a number of photons is very, very hard, right? So this is not interesting. But it turns out that again, once you got this logic, it's easy to map this problem into coherent states, ordinary boring coherent states. So basically, and I'm just not gonna basically bother you with details, but basically the idea is that now instead of Krauss-Max, we have displacement operator, where we increase mean of number of degrees of photons by 1. So it's increasing of mean. It's not adding 1 photon. It's just increasing by a mean of 1 photon. And then the D is our Diophantine equation that we wish to solve. And then observable basically needs to be taken in this form. So that's and then everything else is already said. The displacement operator just adds a mean photon, 1 photon, and the so that will solve that actually. So again, this would be a coherent state that would solve the problem. So this is actually not a Fock state anymore. This is a coherent state. So this is a coherent state that would solve this Diophantine equation. So, okay, so what does this all mean? So far it was great, but PowerPoints don't commute. Really don't commute, between the machines. It got moved a bit. But it's okay, it's not as bad as it could have been. So, it's amazing that if this is established, you can easily generate, I don't know, you guys tell me, this is the simplest, hardest quantum problem you can have. It's a problem involving 2 bosons, but finding the ground state of this, let's say Hamiltonian or observable, is NP complete problem. Just 2 particle problem is NP complete problem in quantum mechanics. And how do we come up with this? Actually, it's a trivial thing. There's a paper, since the Diophantine equation is equivalent to computational, to Turing computations, obviously mathematicians beat the hell out of this Diophantine language in terms of computation, and they found everything, they mapped everything in terms of Diophantine language. Kolmogorov complexities, all these things, classes of computability, etc. So we pick we pick one of those equations, very simple equation that sort of has it's known, whose solution is a P-complete problem, and we constructed one two-body bosonic system which is in P-complete. So it's amazing that actually that thing is as hard as like solving Ising problem principle. Yes.
So the alpha, beta, and gamma integers?
Yes.
Like 62. 157.
Integers.
Okay.
Actually, they're positive integers. In the presentation. So so it's interesting that it's interesting what can come out of this finding. What's the physical meaning of this? Now, so I wanted to say 2 things, and how much time do you have? My phone
Well,
just
we're a
keeps-
little over, but I mean,
I see.
at least 5 minutes, 5 minutes.
Yeah, so basically, I wanted just to repeat some of the things that, basically the physical meaning of the Hilbert 10th problem, solution to the Hilbert 10th problem means that there is quantum control is algorithmically not solvable. in fact, many things, control things, are actually not solvable. For example, state-to-state transformation problem is also not computable because it leads to Diophantine equation of not the same form that I showed you before, but using the same methods, you can show that it's the same problem. So finding a quantum policy to get from desired initial state to desired final state is also generally not doable. Now, what's interesting is that since basically using Diophantine language is equivalent to solving, to making logical statements, and therefore quantum control can be used to actually answer logical conjectures directly. In particular, actually, a Riemann hypothesis can be reformulating also as a quantum control problem. And this is, in my knowledge, the shortest Diophantine equation known to correspond to that. It only takes 2 pages. Actually, it's much more shorter than the previous versions. That basically, if you know a solution to it, you immediately know the answer to the solution to the Riemann hypothesis. Now, and final comment, which is not on the slide, and the most important comment, is that something very important happened in physics, actually, for theoretical physics. I don't know, in physics, but I think it has not been understood in theoretical context. The redefinition of standard units, where basically right now all the units are purely informational concepts, right? There's no anymore kind of objects stored, has profound applications for theory actually. Now every observable, it applies to quantum world especially, everything is right now observable is actually a rational number. It's exactly a rational number because all the constants, fundamental quantum constants, have right now fixed rational values. They're not anymore floating objects, they're fixed numbers, they're exact constants. So therefore, as far as quantum mechanics is concerned, where H bar and E and M rules the world, all the basically Hamiltonian elements, everything, these are matrices over the field of rational numbers. And that's actually, what it means is that we are dealing with the Diophantine language explicitly, because how many rational numbers are out there? As many as integer numbers, right? And so we can actually reformulate. So I think this kind of way of looking at Diophantine language and quantum physics will have much more to unveil actually, especially given the kind of, as I call it, Diophantine coup d'etat that took place last year. Thank you for